Okay. So, we have looked at the usefulness of the rank of a matrix, and we have seen how the rank tells us whether a set of equations is solvable or not, and whether solutions exist, and if they exist, is there a unique solution or are there infinitely many solutions. So, clearly the rank of a matrix is a very useful quantity to have to know, especially when we are dealing with very large number of equations. So, often in many theoretical studies we deal with matrices of very large orders, of the order of the thousands, and we need to have an efficient way to calculate the rank of the matrix. Okay. So, the rank is defined as the number of linearly independent rows or columns of the matrix. So, the obvious way to determine the rank would be that you consider, if you think of a matrix where the elements of the first row, we call them R1 vector, you can think of them as R1 vector. Elements of the second row we think of R2 vector, elements of the third row as R3 vector, and so on. Okay. So, the elements of the first row, all these elements can be thought of as a vector, and we call that vector R1. Similarly, the elements of the second row we call it vector R2 and R3 and so on. Now, we are asked to determine the rank, and we have to find out how many of these vectors are linearly independent. Okay. Now, so the first thing to do is to see if all these vectors are linearly independent. Okay. So, we have a total of, let us say, Rm. So, first we see if all the vectors are linearly independent. So, see if and let me remind you that these vectors are said to be linearly independent if the equation C1 R1 plus C2 R2 Cm Rm equal to 0 has only one solution, namely C1 equal to C2 equal to Cn equal to 0. So, if this equation has only one solution, and that is the trivial solution, and no other solution, then these vectors R1, R2 up to Rm are said to be linearly independent. So, we check for linear independence, and if these vectors turn out to be linearly independent, if linearly independent, then clearly the rank should be equal to m. Okay. And if it is not linearly independent, then the rank is less than m. So, if not linearly independent, then rank less than m. Okay. So, now we have to say what the value of this rank is. The value of the rank is some number between 1 and m, but we do not know what it is. So, then what we do is we take various subsets of m minus 1 vectors. Okay. So, you can take the first m minus 1 vectors, and you can see whether they are linearly independent, and you keep repeating this process. If they are linearly independent, then the rank is m minus 1. If they are not linearly independent, then the rank is less than m minus 1. So, you keep repeating till you reach a set of vectors that are linearly independent, and that is what you identify as the rank. So, we go almost through this iterative procedure. We will first check if rank is equal to m, then if it is not equal to m, then it must be less than m. So, then you check if rank equal to m minus 1 and so on. Okay. Now, clearly you can see that this procedure is quite cumbersome, and you know that you can check whether the rank is 0 of a matrix, but or sorry, you can check if the rank is m, but after that you have to take subsets of these vectors and then try to look for smaller rank. okay, and clearly this procedure will work for if you have a few vectors, but if you have a very large number of vectors, this procedure is not very efficient. And the procedure that is used is something called Gauss elimination. Okay, and this is based on taking linear combinations of vectors. Okay, so it is based on linear combinations. Okay, and I won't go into the detail of the formal procedure. What I'll show is I'll illustrate this through an example. Okay, now suppose you are to calculate example. Calculate the rank of and the matrix is given by 4 minus 1 3 1 3 2 1 minus 9 7 minus 10 9 31. So, you are asked to calculate the rank of this matrix. Okay. Now, while it's worth mentioning now that though I did this with rows, I could also do this with columns, and you can choose to do it with whichever elements you like. If you want to do it with rows, you can do it with rows. If you want to do it with columns, you can do it with columns, and the answer will be the same. Okay. So that is the important point. Now here the number of rows is 3, number of columns is 4. So you say that number of rows equal to 3, number of columns equal to 4. Okay, and this clearly implies that rank has to be less than equal to 3. So it can either be 1, 2 or 3. Okay, and so let's work with the rows. Now in Gauss elimination, if you are working with the rows, what you try to do is to try to eliminate the elements that are off diagonal. So try to eliminate off diagonal elements using linear combinations. So in this case, let's see how this works. So if you take this matrix and you take, here you have a 3, you have a 4. So if you want to eliminate this, you subtract 3/4 from this row. Okay, so you take the second row and subtract 3/4 of the first row. So if you do that, the first row remains as it is, you don't do anything to it. So if I subtract 3/4 of the first row, I'll get rid of this element. Now here if I subtract 3/4, so it's 2 minus 3/4. So I'll call this as R2 minus 3/4 R1. Okay, so from the second row you subtract 3/4 of the first row, and if you do this, you will get 2 plus 3/4. Okay, that is 11/4. Okay, this is 1 minus 3/4, that is 1/4. This is minus 9 minus 1/4, so that is minus 37/4. Okay, then for the third row we want to convert this to 0. So what we will do is R3 minus 7/4 R1. Okay, so from the third row elements you subtract 7/4 of the first row, and what you will get is 0. Okay, and if I subtract 7/4 here, so minus 10 minus 7/4, that is the minus 10 plus 7/4. So, that is minus 40 plus 7 minus 33 by 4. Okay. 9 minus 7 by 4 into 3. Wait a second. Okay, let me make sure I got this correct. So, in this case I had 2 plus 3 by 4, and you had 1 minus 3 into 3, 9 by 4, sorry. So, that should, this is not correct. So, this should read, this is minus 37 by 4. So, 1 minus 3 by 4 of 1. So, 9 minus 9 minus 3 by 4. So, minus 9 is minus 36 by 4. So, minus 39 by 4. Okay. Then minus 1, no sorry, 1 minus 3 into 3 by 4, 3 into 3 is 9, 9 by 4 is, so 1 minus 9 by 4 is minus 5 by 4. Okay. Now, in this case this minus 7/4 of this gives you 0, minus 10 minus 7 by 4 into minus 1. So, that is minus 10 plus 7 by 4. So, that is minus 33 by 4. 9 minus 3 into 7, 21 by 4. Okay, that is 15 by 4. And similarly 31 minus 7 by 4, and that is 24 minus 7, 117 by 4. Okay. So, in this way you have eliminated, by choosing suitable linear combinations, we have eliminated these two rows. Okay. Now, next what we want to do is to take linear combinations and eliminate this element. Okay. So, in order to eliminate that, what we will do is we will operate by, we will carry out the operation R3 minus, now if I add 3 by 4 R2, then I will eliminate this row. Okay. So, then I will eliminate this number. So, in order to eliminate this, I will do 33. So, minus 33 by 4 plus 33 by 4. So, I will get 0. Okay. And notice that this operation does not change this. So, this plus 3 by 4 of this still gives me 0. So, I have 4 minus 1 3 1 0 11 by 4. So, now this operation will not change the second row, minus 5 by 4 minus 39 by 4. And when I do this, so the first row, so the third row element was 0, add 3/4 of 0, I still get 0. If I take this, add 3 times, sorry, not 3/4. If I add 3 times this element, then I will get minus 33 plus 33 by 4. So, that is 0. Here if I add 3 times this, I will get again 0. So, 15 by 4, 3 times 5 by 4 is 15 by 4. So, 15 by 4 minus 15 by 4, I get 0. And again if I do 3 times this, 39 times 3 is exactly 117. So, again I will get 0. So, now by doing various eliminations, we have managed to get one full row to be 0, and there are 2 non-zero rows, and it is not hard to show that you can never convert this row completely to zeros. Okay. So, if you try to do anything, if you try to convert this element to 0, you will make this element non-zero. So, there is no way of converting all these elements to 0, and so we have 2. So, after linear combinations, we are left with 2 rows. Okay. So, these 2 rows are linearly independent, or rank equal to 2. Okay. So, the procedure for finding rank is to keep doing Gaussian eliminations and find out how many non-zero rows survive at the end of this process of Gaussian elimination. Okay. And the process of Gaussian elimination is to try to get zeros in as many rows as possible. Okay. So, you start from the lower triangular part and try to get as many zeros as possible, and you can easily show that this will lead to a rank of 2. Okay. So, because we are left with 2 independent rows. The next concept that we do involving matrices is the concept of the determinant of a matrix. Okay. So, the determinant of a matrix is a scalar the scalar quantity and it is defined only for square matrices. Okay. So, the determinant is only defined for square matrices and it is a scalar, and this is a scalar that appears quite often when we are dealing with various systems of equations, and therefore we will go and we will try to give the formal definition of this. Okay. Now, if you had a 2 by 2 matrix, then if A is a 2 by 2 matrix, then determinant A is just A11, A22 minus A21, A12. Okay. So, the determinant is defined as the product of these two elements minus the product of these two elements. Okay. And you might also be familiar that if you had a 3 by 3 matrix, then the determinant of A is given by A11 times determinant of this matrix, which is A22, A33 minus A23, A32. Okay. So, we took this times the determinant of this matrix, then you take this times the determinant of this matrix. So, that is plus A12 times A23, A31 minus A21, 2331, 2133. Okay. And then plus A13 times the determinant of this matrix, that is A21, A23 minus A22, A31. Okay. So, the point is, once you have the determinant of a smaller matrix defined, you can calculate the determinant of larger matrices, and you can extend this procedure further. So, notice what we did. We started with a row and we took the first element and multiplied by the determinant of the matrix that is obtained by removing this row and this column. Okay. Then you took the second element and you removed this row and this column, and you get a matrix that is A23, A33, A21, A31, and you take the determinant of that. Then you go to A31, remove these two rows, this row and this column, and you get this matrix. So, you take the determinant of that. Okay. So, this is the general procedure, and you can extend this to once you have defined it for small matrices, you can define for larger matrices. Okay. So, now the definition will always involve this quantity, which is the determinant of the matrix obtained by removing the row and the column. Okay. So, it will always involve this quantity. Okay. So, we will give it a name. So, if we preserve the order of the matrix, then this element is called the cofactor. Okay. So, this element is called the cofactor, and notice that in the cofactor you preserve the order. So, if you are looking at the cofactor of A12, the cofactor of A12 is equal to determinant of A23, A33, A21, A31. And you can define the cofactor for any element. You can define the cofactor for this element also. Okay. So, so when you define the cofactor of A12, we preserve the order. Okay. Now, there is another quantity called the minor. So, minor of Aij, okay, is the determinant of the n minus 1 by n minus 1 matrix obtained by removing the ith row and jth column of A. Okay. So, if this matrix A has elements given by Aij, then you can define the minor of any element as the determinant of the n minus 1 by n minus 1 matrix obtained by removing the ith row and jth column of A. So, suppose you have a matrix A11, A12, A1n, A21, A22, A2n, all the way up to AN1, ANN. Okay. If you want to calculate the minor of A22, okay, then what you do is you remove this row, remove this column, okay, and you will get a matrix A11, A13, A1n, A31, A33 up to A3n, all the way up to AN1, AN3 up to ANN, and the determinant of this matrix is called the minor of Ij. So, this is the minor of Aij. Okay. Now, notice that when we calculated the determinant, it is not the minor, but it is sometimes the minor appears as it is. So, if you take what multiplies A11 is the minor of A11, but what multiplies A12 is not the minor, but in fact the negative of the minor, okay, and what multiplies A13 is the minor of A13. So, this quantity which is sometimes equal to the minor and sometimes equal to the negative of the minor is called the cofactor. So, cofactor of Aij, and this is denoted by okay. So, this is denoted by Aij, capital Aij, and this is equal to minus 1 raised to I plus j Aij or Mij. So, it is minus 1 raised to I plus j of Mij. Okay. So, the cofactor is related to the minus in this simple relation, and now we can write the determinant of A. The determinant of A is nothing but the sum of the elements of each of the row times the cofactor of those elements. So, it is nothing but sum over j equal to 1 to n Aij times cofactor of Ij or A1j. So, you can take the first row. So, I have used the first row for the calculation of the determinant, okay, and actually I can take any row, I do not need to take the first row. Okay. I can calculate the determinant using the second row or the third row or any other row, and also you need not use rows, you can also use columns. So, I can use the first column, I take the sum of elements multiplied by their cofactors, sum of element of A21 multiplied by cofactor of A21, sum of and then A31 times cofactor of A31. So, I can do it even column wise or row wise, and this is very useful because sometimes it's fastest to calculate a determinant using some particular row or column. Okay. So the cofactor turns out to be a very useful way, and this definition of the determinant is what is the useful definition of determinants, especially when you are dealing with matrices of very high order. Okay. Now a thing to note is that each term in the determinant, if you look at the various terms, this is A11, A22, A33, then you have A11, A23, A32. Okay. So each term in the and then if you look at this term A12, A23, A31, A12, A21, A33. Okay. So each term in the determinant has a form. So each term in the determinant looks like A1 and some element I will say I, A2 second row and some element j which is not equal to I, and then A3 k where k is not equal to I or j. Okay. So notice that each element has this form where it looks like A1i, A2j, A3k where I is not equal to j, not equal to k. So I, j, k are all distinct. Okay. So I is not equal to j, I is not equal to k, and j is not equal to k. So each term, each element looks like this. Okay. And so the determinant looks like a sum of terms of that form, and but some of them have a positive sign and some of them have a negative sign. Okay. And this inspires another way of writing the determinant as a sum, okay, of various terms of the form A1i, A2j, A3k and so on up to if you have an n by n matrix, then it is n j k l I'll just call it nr. Okay. So where I, j, k etc. are not equal to each other. So each of them are distinct. Okay. And you sum over all possible such combinations. Okay. And there is an index. So sometimes it is plus, sometimes it is minus. So there is a factor called, I will write it here, it is called, so you multiply this by p of I, j, k up to r. Okay. So you sum over all possible terms of this form. Okay. But sometimes p is plus 1, sometimes p is minus 1. Okay. And this p is called the permutation index. Okay. And this permutation index can be plus or minus 1. Okay. So this permutation index is plus or minus 1, and it is equal to plus 1, then you call it an even permutation. If it is equal to minus 1, you call it an odd permutation. So p of I, j, k up to r is equal to plus 1 or minus 1. Okay. And this is called the permutation index. And sometimes this is written as p is equal to minus 1 raised to p. I will call this p prime, where p prime is the number of permutations that need to be carried out to get the sequence I, j, k up to r from 1, 2, 3 to n. Okay. So what this means is, suppose you have a term in the determinant that looks like a1 3, a2 1, a3 2. Suppose you have a term that looks like this, okay. Then this sequence I, j, k up to r is basically 3, 1, 2, okay. And now you have to see how many permutations you have to do to get 3, 1, 2 from 1, 2, 3. So, you start with 1, 2, 3, okay. Now, if I switch 1 and 2, so first I switch 1, 2, then I get 2, 1, 3, okay. Then I switch 3, 2, okay. Then I get 3, 3, 1, 2. So, therefore, I have to do 2 switches. So p prime equal to 2, okay. So, p prime equal to 2 means you have minus 1 square, that is plus 1. So, this term will appear with a plus sign in the determinant, okay, and you can easily verify this, because this term is if you take a 3 by 3 determinant or 3 by 3 matrix, a1 3. So, this is this term multiplied by a21 into a32, and clearly this should appear with a positive sign, okay. And you can verify that, because p prime is 2, minus 1 raised to p prime is plus 1, and therefore, this permutation will appear with a plus sign, okay. So this permutation method works is another way of calculating the determinant of a matrix, and typically when you are dealing with large matrices, then some of these methods are quite useful. However, it is it might be fairly interesting and intriguing for you to know that if you are calculating the determinant of a large matrix, and when I say large, I mean greater than 10. I mean 10 is also large enough, okay, but any matrix larger than 10, then it turns out that this way of calculating the determinant using cofactors minors turns out to be much less efficient than a method of Gauss elimination, okay. So that's that is something that you should know whenever you are numerically calculating the determinant of a large matrix, then it is always better to use Gauss elimination, okay. Now, why is Gauss elimination useful for calculating the determinant? So, in order to see why Gauss elimination is useful for calculating the determinants of matrices, let us write down a few properties of determinants. So, a few properties of determinants. So, the first one is you can calculate, so determinant of a matrix can be calculated using any row or column. Of the matrix. So in the examples that we looked so far, we were always using the top row or top column, but you can calculate a determinant using any row or column, okay. Next is, and this it follows from the definition of the determinant, that the determinant is unchanged if the rows and columns of the matrix are swapped. So, in other words, if I had a matrix that looked like A11, A12, A13. Let us just take a 3 by 3 matrix, A21, A22, A23, A31, A32, A33. Now, if I change the rows into columns and columns into rows, then the matrix I get is called A transpose. So, this matrix is called A transpose, and this is given by A11. Now instead of A12 I put A21, A31, and then what I have done is I've instead of putting A21 here, I will put A12 here. A22 will remain the same. Okay, so I have A12, A22, A32, and then I have A13, A23, A33. Okay, so this matrix is called A transpose. Notice that we have interchanged the off diagonal elements, but the diagonal elements are unchanged. Okay, and it turns out that determinant of A equal to determinant of A transpose. Okay. So, determinant is unchanged if the rows and columns of the matrix are swapped. The third property is that determinant equal to 0 if any row slash column contains each element to be 0. So, a determinant of a matrix is 0 if any row or column contains each element 0, contains has all elements 0. Okay, so if I have and this is very obvious to see, if I have 0, if I have any one row or column to be 0, then I can always calculate the determinant using that particular row or column. Okay, and I can so if I had the first column as 0, I would calculate the determinant using this column, and so I would multiply this by its cofactor. So, and then this by its cofactor and this by its cofactor, and since each of these are 0, the determinant will be 0. Okay. Okay. Now, the next property is probably the most useful property of the determinant, okay, and this is that determinant of a matrix equal to 0 if two rows slash columns are identical. Okay. So, if any two rows or columns are identical, then the determinant of the matrix is 0. So, and that is also fairly obvious to see, because suppose let us say these two columns were identical. If these two columns are identical, then I can always calculate the determinant using this column, and the cofactor, each of the cofactors will be 0. So, if these two columns are identical, then the cofactors will be cofactors of elements of this row, this column will be 0. So, the determinant of a matrix is 0 if two rows or columns are identical. Next, determinant of a matrix with two rows or columns interchange is minus 1 times determinant of of the original matrix. Okay. So, suppose I take a matrix A and I calculate its determinant, and then let us say I swap 2 rows or I swap 2 columns of A, then the determinant of the resulting matrix will be -1 of the determinant of A. Okay. And the last property that follows from this property is that determinant of a matrix is unchanged when we add to any one row or column a scalar multiple of another row / column. Okay. So, what I mean is, suppose I have a matrix A which is like this. Now, to each element in A I add a scalar multiple of some other row. So, if I have A is equal to 2 3 and if I have A prime, so I take, let us say I to the first column I add 5 times the third column. A13, A21 plus 5, A23, A31 plus 5, A33, and I have A12, A13, A22, A23, A32, A33. Okay. So basically I kept everything else same, but to one row I added a scalar multiple of another row. Then the determinant of A prime equal to determinant of A. Okay. So the determinant of A prime is equal to determinant of A. Okay. There are some other properties of determinant. Suppose I take a determinant of a sum of matrices. So if I construct 2 matrices of the form, okay. So the reason why this is true, is that the determinant has the property that the determinant of this matrix A is equal to the determinant of a matrix where you just take A11, A21 and A31 here, okay, plus a determinant of a matrix where you just put this term. Okay. So this gives us this is another property of the determinant, and it's important to be a little careful here. Okay. So suppose I have A11 plus 5, A13, A21 plus 5, A23, A31 plus 5, A12, A13, A22, A23, A32, and I will call this A prime. Okay. So the property of the determinant is that the determinant of A prime is equal to the determinant of A. Okay. Now buried in this are two other interesting properties of determinants. Now the determinant of this matrix A prime is equal to determinant of this matrix, where whenever whenever you have something like this where you have sum of terms, okay, you can write this in this form. Okay. So determinant A prime is the determinant of this matrix, which is just A, plus determinant of, okay. So you had this plus this, okay. So this is the property of the determinant, that if you add an element, if you add elements to one row, then you can split the determinant into these parts, okay, then you can add the determinants. Now remember, determinant of A plus B, if you add up two matrices, the determinants of the sum is not determinant sum of determinants. So if you add up matrix A plus B, then determinant of A plus B is not equal to determinant of A plus determinant of B. So this is not true. However, if you just add elements to one row, then the determinants can be added in this form, okay. The other property is that the determinant of this matrix is equal to, so whenever you add one elements of one row, you multiply it by a scalar, then the determinant gets multiplied by the scalar. So 5 times determinant of A13, A23, A22, A23, A33, A32, A33. Okay. So whenever you multiply all the elements of one row or a column by a scalar, then the determinant of the whole matrix gets multiplied by that scalar. So determinant of this matrix is 5 times determinant of this matrix without the scalar. Okay. Now the determinant of this matrix, because two rows or columns are identical, so in this case the first column and the third column are identical, so the determinant of this matrix is 0, okay, and therefore this whole part is 0, and so determinant of A prime becomes equal to determinant of A. Okay. So in the next class we will see how we use determinants in where they appear in the solution of a system of linear equations.